So traditionally, there are two schools of studies. One is on the individual strategy, individual structure of the bridges, mainly using the finite element analysis to determine the traffic capacity of the bridges by different regulatory strategies. Another one is the network protection strategy, which is essentially a network design problem, as you're probably all familiar with. But for the second strategy, most of the time we adopt greatly simplified relationship between the bridge capacity and the retrofit cost. So most of the time we assume this is a linear relationship. But from structure assessment perspective, definitely it's not. It's actually more complicated than that. So because of this knowledge gap or modeling gap, this actually motivates this study. So we combine the network design and individual bridge assessment by using finite element analysis into this bi-level modeling structure. On the network level, upper level, we look at the strategy to allocate the limited amount of money to different bridges to make sure that the system will bear the minimum retrofit cost as well as the travel cost. Okay. At the lower level, we use the finite element analysis to determine the maximum traffic capacity with the allocated money. Okay? And the resulting traffic capacity will be feedback to upper level. So this is an interactive process. And this is actually a collaboration with one of my colleagues in the structure assessment. But here, due to the time limits, I'm going to focus only on the upper level, network level, with a special attention to the risk assessment integration system planning process. So if you still remember the four general methods that I just talked about probably 10-15 minutes ago. So here I'm going to demonstrate two of them. So the top one is the two-stage stochastic programming method. The decision U is the first stage decision. Basically, it's the retrofit strategies. And this is defined by this capital U set. And again, I wouldn't go into the details. And then the recourse function Q, in this case, is the travel cost function. It's actually explicit travel assignment problem. And we use BPR function to estimate the travel cost on each link. And the travel cost, the capacity of the link depends on two things. First, if this bridge is at a risk or not. If it is at a risk, then it also depends on the strategy, the retrofit strategy used. So as you can see, this problem is non-convex because of this involvement of the first stage variable on the denominator, which is really bad from the mathematical standpoint. Another term is here. This is a bilinear term, so this is a cross product of two variables. So this is a nonlinear mixed integer problem. Okay. So now we're gonna make it even worse. We introduce this C-bar term, which so how many have you heard about C-bar? It's what we call the conditional variable of the risk. So this just penalizes the scenario with large losses with a preset confidence level, let's say 95%. Then alpha will be equal to 95%, and so on. And then we're going to combine this C-bar term with this two-stage stochastic programming to form what we call the mean risk model by introducing a coefficient line. So through the simple manipulation, we have this the mean risk stochastic programming problem, and then we first we linearize this max function here, and then we introduce eta, which is the value of the risk. So this problem from the first slide is very similar to the two-stage stochastic programming problem, except that we have this additional C-bar term here. However, because of this the value of the risk eta, which is scenario independent. So in other words, we actually introduce additional first stage decision variable. So that makes the problem even worse. So actually, another contribution of this study is to develop this hopefully powerful solution method to solve this problem. So we actually involve two steps. First, we need to convexify this Q function, which is non-convex, and this is the origin of the complexity of the problem. And then after that, we apply this generalized Bender's decomposition to solve this problem. Again, there's a lot of details in that. Actually, in our paper, probably 1/3 of the paper was devoted to this step to convexify this Q function. So this is a collaborative research work with one of my colleagues from the mathematics, and he's specialized in nonlinear programming problems. Okay. And then we combine, then we apply our developed generalized Bender's decomposition method and compare with the results of the bombing, which is a commercial solver for mixed integer nonlinear program problem. From the results, we can see our method is much more efficient than the commercial solver with very good quality. So then we apply this method to this Sulfos network, and a lot of results, but to our most of the interest is to compare why we need to bother so much to develop this mean risk model. So that's why we compare our solution with the 2 stages of stochastic programming. Okay? So this is the results of both. And of course, the mean risk stochastic programming method really depends on the coefficient you pick, the confidence level, and also the coefficient linking the 2-stage and C-bar. And from this result, we can see mean risk model is more risk averse with a higher or increased retrofit strategies. But that will help to lower the travel cost for long term. In the end, they have in general lower total expected cost than the 2-stage stochastic programming problem. Okay. So let's refresh, and then we move on to another new topic, and this is more recent. Alternative refueling network design. And specifically, I picked the EV charging because this is actually driven by 2 sides of the story. On one side, reduce the increase of the electric vehicles riding on the streets. Especially, you probably know that Atlanta is the 2nd largest city in this country having EVs. You probably see the Nissan Leaf running on the street almost everywhere. On the other hand, compared to the gas stations, we have very limited charging stations on the network. Okay, and a couple of the challenging is the limited vehicle range. So let's take the Nissan Leaf again as example. So the Nissan Leaf, the latest model still have about 84 miles. This is the number published by EPA. So let's say if I want to travel from Clemson to Charleston, which is about 240 miles away, I need to charge at least twice to get there. So meaning that we have to, strategically set up charging stations on the highway network to facilitate the long distance travel. So you probably know Nissan Leaf is mainly for what they call city cars, just for work commute in urban areas. So whatever you want to extend it to larger, or the only vehicle you probably want to own for a household, then you have to have the public charging stations. So that's why, from a research perspective, we just need to develop a compatible charging network. So this compatible charging network definitely needs to take the geographic distribution of the network, like the trips distributed on the network, and also the topology of the network. And it's definitely a stage of decisions because charging network and the number of electric vehicles is always a chicken egg problem. Which one should go first? So most likely you have to develop the infrastructure gradually to accommodate the growth of the EVs over time. And of course, when you estimate the future demand, it involves uncertainty. So that's why these 3 factors definitely have to be considered And actually, those three factors have been considered in our recent the spatial economics models. And right now, we are doing the last one to incorporate the mobility traces. So for example, the chance of charging. So most of the time, when we develop the model only based on the geographic distributions, we probably end up with this phenomenon that if the charging station there, but never used, because we just base our decisions on the geographic distributions. So we have to, in order to develop the strategies that will compatible with our people or humans' behaviors on a daily basis, we have to understand mobility of that. So there's a series of models, and all the models are actually based on this fundamental one, what we call the multiple path refueling location model. So the idea is, let's use these two single graphs to represent the idea. So on the top, if we just want to travel on the shortest path between all the node pairs, in this case, given vehicle range of 15, we have to have 3 charging stations. So you can probably take a second to look at this graph. Why we have to have 3? From A to C, we have to charge B. From A to C via D, we can do that. And from A to G, we have to charge a D. From E to G, we have to charge F, and so on. Okay? So this is based on the shortest path. So now, if we just relax this assumption a little bit, so we assume that people actually can tolerate a little bit deviation from the shortest path, let's say 20% maximally. Then, from A to C, instead of going the shortest path, people probably would like to take A to D to C. Similarly, from E to G, instead of going this way, people probably would like to take this route. So in this case, we actually save 2, so we just need 1 charging station here. And this is actually pretty realistic because right now all the people have this, mobile phones. They have the mobile app application. So if you type origin destination, it will give you 3 choices, right? So which means the information is actually available for drivers. And of course, this is a trade-off between the convenience and the cost effectiveness for the system. So based on this idea, we developed this again MPRLM. Sorry, not good acronym. And again, no details. I just want to highlight the sections of the constraints and of course the objective function. So we have this refueling and consumption conservation constraints, logic constraints, and the multipath definition constraints. And based on that, we developed this, on top of this fundamental model, we extended to multi-stage and as well as the probabilistic model. So multi-stage is to capture the station decision process, and the probabilistic model capture the uncertainty in estimating demand. So, so here we just demonstrate the multi-stage model, which is based on, is pretty driven by the market. So we actually use the multivariate logic model to estimate, the future demands, which is a regressional logistic model. It's a regressional logistic model. And of course, this is a pretty rough estimate. I believe if you spend more efforts on estimating the future demands, we probably end up with uncertainty with a multi-stage decision process. So let's say if we assume that the statistical analysis is corrected, now this is a deterministic model. So we have this cost of establishing new stations as well as the cost of relocating existing stations over time. And additional constraints are introduced. Here basically is just to establish the relationship between the space and the time on the spatial resolution over time. So X and Z. So X is just the status of the charging stations on network. So meaning like where they are, how many there are, and Z is the relocating strategies. So this this constraint describes the relationship between the two. And then we apply the model to in the supply highway system. So in this case, we assume the 3 stages. Stage 1 is that we have 15 cities in South Carolina already have the charging stations available, which accounts for 34% of population in the state. And the second stage, we assume that we want to reach 50% of population covered. So that results in 13 cities introduced, additional 13 cities introduced. And the last stage, we assume that entire population can be covered. So that accounts for 94 cities in South Carolina. And this is the results. So stage 1, the green dots represent the public charging stations on the highway network. And the stage 2, you probably noticed that there's no change at all. The same 9 charging stations can be used to serve additional 13 cities. The reason is those 13 cities highlighted by this the squares, the blue squares, are actually quite close to the existing metropolitan areas. So that's why, from the spatial distribution perspective, there's no big change. And then the last stage, we introduced 2 additional charging stations, mainly because these last stage cities are still clustered around metropolitan areas. So we just need an additional 2 charging stations. Okay. And this work has been published in this Transportation Research Party. Probably last one or journal, I forgot exactly. But it's published. So that includes definitely more detail. So that includes the heuristic method we developed for solving this large-scale problem as well. Okay, so the last one. This is actually brand new, and this is still ongoing. This is what we call the crowdsource-based delivery systems. So I believe all of you are familiar with Uber, and this is actually the Uber version of good delivery. So most of the time, people are talking about, when they talk about this is a short name for this, is what we call the crowd shipping. So when we talk about crowd shipping, most of the time people say, well, this is inspired by Uber. But I have a different story. So for people from India, you probably all know that in Mumbai, this is what they call the double wallets. So how many? Have you heard about this? Yeah. So I was quite inspired when I first heard about this story when I was a student. So this basically is a lunchbox delivery system. They use millions of lunchboxes every day, from households to workplaces. And more amazing about this system is there's no computer involved. It's pure man-powered system, and they actually use different kinds of transport modes. They have, I don't know what they call it. It's like sort of bicycles, and larger, definitely, can carry a lot of boxes at the same time. And then they use the trains in the system. And it can be punctuated. I mean, they just so stick to the timetable. So amazing. And what people right now try to develop is something like this. But of course, instead of only delivering lunch boxes, we want to deliver all different kinds of goods. And this is what we call the crowdsourced delivery system. So basically the idea is we group people together and do the delivery for you. So there are a lot of startup companies, mainly in the Bay Area, such as Deliv, Zipment, which is actually headquartered in New York, recently acquired by Deliv. And then Instacart and Postmates are those what we call grocery delivery companies. You put your orders online, they will go to Whole Foods and then pick up the things you ordered and deliver to you. But the idea is very similar to this. But compared to this double wallets delivery system, all these systems is pretty intuitive. They just do one-to-one delivery for now. This is just for easy operation. But from the optimization perspective, it's quite trivial, I would say. But I believe this area is actually growing. And this is how I view this problem. So this is a traditional pickup delivery system. You have this depot, you have pickup points, delivery points. So like a UPS, they leave the depot and do the delivery to pick up along the route. And of course, this system, most of the time, with a fixed scheduling, with a fixed routing. Okay? So now, this emerging crowdsource-based delivery, we have totally random delivery requests. And it can be random in terms of location, it can be random in terms of the time. Okay? So as I just mentioned, now they just do one-to-one delivery. What if we want to improve this system? What if the system becomes larger? We have to have more power sources, manpower sources, or we can do something internally smarter. For example, we can probably do consolidation of deliveries, meaning that, for example, this different color represent different vehicles. In this case, we use 2 vehicles to deliver 4 different requests. Okay. So, for example, for this one, the red one, all the way to the destination, actually pick up another delivery and do the delivery first, and then come back to the original delivery. Of course, these 2 deliveries geographically should be close to each other, or not so far away from each other. Or they can do delivery first, and then they can do a second delivery on the route. Okay. So now the problem is, this new challenges in the crowd shipping is totally dynamic and is totally random. So most of the time, if we want to do something more sophisticated, we're actually facing the challenge of rematching or rerouting in-route vehicles. And we can make the system more complicated or more efficient if we can introduce heterogeneous transfer modes. For example, if you remember the Zigman, most of the deliveries were made by bicycles. They do this small community delivery in Manhattan areas, and most of the time by walk or by the bicycles. What if we combine these 2 systems? Let's say we have these bicycles do small area or small community delivery